Welcome students, and in this video we are going to talk about the first order general PDE, right? So let us just write it down. First of all, it should look like this, right? So I am going to start with a semi-linear equation first. Yes. So x y u ux plus b of x y u uy minus c of x y u equals to 0. So this is a general form of a first order equation. Actually, it depends on a, b and c, a and b, but generally speaking, this is actually a quasi-linear equation. Yes, but we will start with this equation for all purposes. Okay, now the thing is this, this is the problem, right? Now, let me first recall what we want. See, here, let's say we have some hypothesis, right? We have some hypothesis. So what is our hypothesis? So we are going to assume, see, A, B and C, they are functions, right? From R3 to R. Yes, so we have to put some assumptions in here. See, A, B, C, where are they from? See, X and Y, here we will always be assuming XY is from some domain D, which is subset of R2, right? So we are just writing this equation in R2. So first of all, X and Y is in R2 and U of XY is again in R. So basically this is from R3 to R, right? Okay. Again, what is happening? See, A is a function of XY. X is in R. Y is in R. And U if I'm writing, it should actually write, I should write it like this. It is U is a function of X and Y, right? This is the U which we need to find out. Again, this is also in R. Okay, that's the unknown. So essentially A, B and C are function from R3 to R, and we are going to assume that they are smooth. Clear? What do I mean by smooth? I mean at least C1. So basically all the partial derivatives of A, B and C exist and they are continuous. Clear? Okay. So now let's say what we are going to do is this. We are trying to find a solution. And what is the meaning of a solution? So what do I mean by a solution here? If you look at the equation, see, let's say A times some quantity, right? Plus B times some quantity, minus C times equals to 0, right? So you see here, forget about this ux, uy, this quantity. Yeah, essentially A is a continuously differentiable function, C1, right? B is a continuously differentiable function and C is also a continuously differentiable function. Yes, and we want our u of x and u of y to exist. Yes, in such a way that the sum is equals to 0. 0 is again a smooth function which we can think of it as a C1 function. So essentially by an equation we are actually looking for ux and uy to be at least C1. So continuously differentiable. So you understand what's happening. See, if ux and uy are continuously differentiable, so this is C1, A is C1, so the whole thing is C1. Again, uy is C1, B is C1, so the whole thing is C1 and C is given to be C1. So the sum of three C1 function is actually going to be C1, which is 0. So it makes perfect sense. Huh? So with this idea in mind, what we are going to do is we are going to define the notion of solution here. So what is the solution? A solution, yes, a solution U. I am going to assume U is C1. So basically ux and uy both are continuous. Yes. Of course, you can take C2, C3, does not really matter. C1 is the minimum we need. Yes. See, this is C1. If U is C1, ux is continuous, this is continuous, this is C1. Again, C is C1. So the whole thing is definitely continuous, which is equals to 0. So 0 is the continuous function, right? So you can assume U is C1. Of course, you can assume it is C2 also. It's not an issue. But for all purposes, now we are going to assume it is C1. C1 of where? C1 of D. Yeah. Now, it is not a guarantee that we can find a solution in the whole of D. Yeah, but still this is the general notion which we are going to start with. Yes, so basically we are trying to find a function which is defined on all of D in such a way that they are continuously differentiable, the function. Yes, okay. And moreover, what happens to the function? So basically we are looking for that function to satisfy this thing, right? xy, u of xy plus b of xy, u of xy, oh, I have missed here u x of x comma y. Okay, so maybe I can put it here. One second, let me just put it there. There is no point writing it like this, so maybe I can put it here. So we have a times ux at the point AB, okay, plus b times xy, u of xy at the point AB, and then uy of xy, right? So basically for every point xy, I want my equation to be satisfied. That's the point, okay? So minus c of xy, u of xy has to be 0. I hope it is clear now. For every point x and y in the domain D, this should be true. That's the idea. Okay, so that you see, that is the requirement which you are putting. It may happen that we may not find a solution like this. Basically, this sort of solution is called a global solution. Why? Because we are getting the solution in whole of the domain. Yeah, it may not always happen. Okay, so now the thing is this. See, essentially what we are going to do is this solution will be is this form, right? See the solution. So okay, let us understand this thing. See, the solution is a two-dimensional function. So basically u is from D, which is a subset of R2 to R3, sorry, R, right? So what is the graph of u? If you just look at the graph of u, that is a subset of R3. Okay, so the graph of u will lie somewhere here. Okay, graph of u. So you understand what's happening here. For every xy in the this R2, so let's say x and y, there is a z, and this z is what? Z is the height corresponding to the graph. So basically z will be equals to u of xy. Okay, so essentially what is happening is this: we are trying to find a solution u, and we are going to look at it in a geometric way. So what we are going to do is, corresponding to that solution, there is a graph of that function, right? Corresponding to that function. Okay, so you see, so let's say let S be the surface, okay, surface corresponding to the graph of this function, graph of z equals to u of xy. I hope it is clear what I am trying to do here. See, we need to find u, right? And the thing is, u is from R2 to R. So essentially, in the graph of a function, if you just look at it, what is happening is that will lie in R3. Yes, so that is basically nothing but a surface. Yes, and the thing is this, you see, any point on that surface is given by xyz, where z is u of xy, right? Yeah, that is clear. Okay, so you see, any point on S is given by, which is x, y and u of course x and y, yeah, u of x, y. So at this point, let's say this is the point, right? U, y and u of x, y. You can also write it as u, y and z. That's not a point, but let us just stick with this u, y, u of x, y. You see, the thing is, if you look at the gradient vector at that point, the gradient vector okay, of the capital F, okay, so gradient vector of capital F, which is given by f of x, y and u, which is u of x, y minus z. Okay, so essentially, you see, the thing is this, see, what we are doing is this. First of all, of this function, what we are doing is this. You have a solution u, and that solution, if we want to draw the graph of that function, that will lie in R3. That is a surface, yet, and so that is nothing but the label set of a function capital F, right? So you see, what we are basically doing is, we are looking at S as a level set, as a level set of this small, the big function capital F, x, y and u. Clear? And label set corresponding to the height 0. Yes. So the gradient vector of this capital F is given by okay, what is the gradient vector? If you remember, gradient of capital F is nothing but capital F of x, capital F of y, and capital F of u. Yes. Which, if you want to write it down, is ux, uy, and minus 1. See, z is nothing but u essentially, right? So it is minus 1. Yeah. See, f with respect to u is this is see this z, right? See, so this is u I am writing. This f is a function of x, y, z, right? So I should write, one second, there is a small notation mistake. I should write it as u, otherwise you may get confused, but you do realize z is actually u. So this is u. Okay, right. So that is ux, uy, and minus 1. Yes. So you see, the thing is this gradient is what? It is normal to the surfaces. Yes, we know that, right? So basically, let's say if the surface is given by the level set of some function, then the normal at any point is given by the gradient vector, which is this. Yeah. So if you don't know this, please go back to your several variable calculus course and just look it up. It is very easy to prove. It's not a very difficult thing to do. Okay. Right. Now, if you just look at the equation, see what is happening here is this. 1 can be written like this, can be written as a of xyu, comma b of xyu, comma c of xyu, okay, and this vector dot ux at the point xy, I am not writing that part, uy and minus 1 equals to 0. See, this is nothing but this, right? So essentially, you see, this is the normal vector. See, this vector, this is the gradient vector, right? And that is normal to the surface. Is it okay? This is the normal to the surface. Okay. So what is happening is this u is a solution if and only if the directional vector, right? So that implies that the direction vector, what is the direction vector here? A, B and C, right? Direction vector, which is A, B and C. I'm not writing A, B and C are functions, right? But I'm just writing it like this. Lies on the tangent plane. Of the surface S. Yes. See, again, look at it. See, what is happening is this. You have this surface, right? And this point, for any point x, y, at this point, the gradient vector is given by the gradient of capital F. Yes, gradient of capital F. What is A? Capital F? Capital F is given by this. Yeah. Now, you see what is happening is this. If this is the gradient vector, which is given by here, ux, uy and minus 1, right? And the equation which we have in our hand can be written like this. See, the field ABC, the dot product with this normal vector. So essentially what that means is that if you look at the tangent plane at this point, the field ABC must lie on the tangent plane, right? That is why it is 0. So basically they are perpendicular to each other. So that should, since this is the normal vector, this has to be on the tangent plane. Okay. Okay. So of course this is true where gradient of capital F is not 0. Just the assumption basically of capital F. Wherever this is true, so if gradient of F is not 0, this is always true, right? Okay. So you see, how do we put all of this together? A curve in x, y and u space, which is z basically, yes, but I will write it like this. See, this is z. So x, y, u space, okay, whose tangent at every point okay, coincides with the direction field. Yes, and this direction field ABC, this is a direction field. We will call it a direction field basically, and we will call it a characteristic direction field. Why characteristic? Because you see the whole equation is actually determined by ABC. If you change ABC, the equation changes, right? So basically we call it a characteristic. It coincide with the characteristic direction field. Direction field ABC is called the characteristic curve. Called the characteristic curve. Okay. So essentially what I am doing is this. Now we understood that the surface which you are looking at is such a way that the point on the surface. So if you at any point, if you look at the tangent, ABC lies on that tangent plane, right? So now the question boils down to this. If you have a tangent plane, if you know that there is a vector field which lies on the tangent plane, can you construct the whole surface using that information? Yes. So what we are doing is this. Essentially, we are first of all, looking at a curve which lies on the surfaces. You understand that curve? We are going to call it a characteristic curve in such a way that a point. So basically, what we are doing is this. See, this is your, let's say, surface, right? That's your S. That's your solution surface. Okay. So this is given by z equals to u of xy. Okay, or u equals to u of x. So it doesn't really matter. U and z are basically same. Okay. Now you see at any point what we are saying is this. There is a tangent plane. Why there is a tangent plane? Since u is continuously differentiable, this surface also admits a tangent space at every given point. Yeah, that is true. This is our from our basic curves and surfaces course. So if that is the case, so you see what is happening is this. I want to construct this surface with this information, and I know that the ABC, this direction vector, okay, for a fixed xy, that is xy and u, this direction vector lies on the tangent plane. This is what we know. So what we are doing is, first of all, we are looking at a curve. Okay, let's call the curve C. C is such that it lies on the surfaces. You understand? Yes. And what is happening is this. What is the characteristic of C? What is the identification of C? C is such that at this point in C, yeah. So if you look at the point x, y, and u, what is happening is this. The tangent vector. See, if C is there, which lies on S, okay. So CE will be written like this, right? X of t, y of t, and z of t. If you understood what I am trying to say, and t is in some r. That's how we parameterize a curve in R3. Yeah, because the surface is in R3. Okay, now you see what is the identification. So what is so special about C? C lies on S. Okay, so that is why it looks like this. So this Z is nothing but u of x of t, y of t, right? That's your C. Okay, now C has this property that the derivative of C, is it okay? The derivative of C, okay. So if I am looking at x prime t, y prime t, z prime t, yeah, z prime t. So you do realize that will be nothing but A, B, and C, right? Yeah. So you understood what I'm saying, right? Because the derivative will be the tangent, right? So essentially what we are going to do is we are going to look at a curve C such that tangent is given by this ABC. It's okay, because ABC is the vector which lies on the tangent plane, right? So we can of course think of as a curve which lies on S such that this happens. Is it okay? Once we can find, so now you see from here you know what is x prime of t, what is y prime of t, what is z prime of t. Once you get it, what happens is you just calculate the whole time and you get C. Yes. Now how do you get the whole surface? Once you get the C, what you do is you see you got one curve, right? Now you can go on doing this thing for all possible curves. You understand? And you will end up getting the whole surface like this. Yes. How do you do mathematically this one? Let me tell you. I hope the idea is clear, right? It's very, very geometric idea. Okay. So, see, the thing is this. The tangent vector to the curve, the tangent vector to the curve, as I have already mentioned, tangent vector to the curve, okay, the characteristic, okay, and it's called the characteristic curve and is parameterized by, as I have already mentioned, parameterized by t, parameterized by t, okay, that is how do you write it? X of t, y of t, z of t, and t is in R. Is it okay? Now you see the tangent vector, okay, to this curve, which curve? C, is given by x prime of t, y prime of t, and u prime of t, okay, u prime of t, okay. Of course, u is a function of x and t again, yes, and of course this must be equal to, as I have told you, equal to a, b, and c. Clear? So therefore, we end up with a system of ODE. So we end up with a system of ODE. ODE. Okay. Given by, how is it given? Given by x prime t equals to a of x, y, u, y prime of t. Please remember this thing. This x, y, I am writing it like this, but they are all functions of t again. Okay. So this is b of x, y, u, and z prime of t is c of x, y, and u. Is it okay? These three equations, so the above equations are called the characteristic equations. Equations are called the characteristic equation. Characteristic equations, okay, of 1. So given the equation 1, if I wanted you to write down the characteristic equation, this is what it is going to look like. This three equation 1, 2, okay, 2, 3, and 4. Clear? So this is how we write down the characteristic equation. Okay. So now I hope the idea is quite clear, right? Okay. Now maybe I can give you a little remark. Let's give you a small remark here. Remark A. See, the thing is this idea, this geometric interpretation, one can generalize for higher order PDE. Okay, higher order PDE. So we can generalize this for a higher order PDE. Okay, but it is you do realize what is happening even for this PDE. The visualization is in R3. You understand? So if you are looking for a higher order PDE, the visualization will be not possible. So basically that will be more than 3 dimensions. Okay, right. Another thing is this. See, we started with a quasi-linear equation and not a non-linear equation. Yes. So what happens in a non-linear equation? Can't we do this? Okay. So you see the geometric interpretation. So in case of non-linear equation, let me write it down. In case of non-linear equations, the geometric interpretations. So you can actually have similar sort of thing. Okay. But I mean, not exactly similar, of course. See, the geometric interpretation, let us write it like this, GI, geometric interpretation, is complicated. Of course, more complicated, right? Because this is nonlinear complicated. Clear? Okay. And the thing is this, here we'll have something called a Monge cone, which we will discuss, I mean, maybe in a later advanced course, not in this course. Okay. This is out of the scope of this, I mean, this particular course. So we are not going to discuss the non-linear problem, but you can actually do similar sort of thing, of course a little more complicated way. Okay, right. Now, so let's look at it. First of all, the geometric idea is clear. Now we start with something called a method of characteristics. This is what we actually were trying to prove. The method which we actually did, it's called a method of characteristic. Okay, so first order equation, whenever you have first order equation, it is better to use the method of characteristics. Okay, and by the way, this method is due to the great mathematician Lagrange. Okay, so I hope you have heard about Lagrange multiplier. This is the same Lagrange. Okay, right. So let's say we have this equation 1, right? So what is the equation 1? Which is this, let me again write it, ux plus b of xyu uy. So please understand this thing, we are actually assuming that we are actually assuming here that A, B, C are smooth. Smooth means C1. Yes? Okay. Now, let's say that the general solution, okay, so let's call this as star. Yeah, we want to solve this. Say the general solution. What do I mean by general solution? So basically all possible solutions. We are basically looking at a family of solution which contains all possible solutions of star, if possible. Let's look at it. Okay, so the general solution of star is given by what is it given by? Some function of phi and psi equals to 0. Yes. Okay, so what is f? What is phi and psi? Where f is an arbitrary function, okay, of course smooth we will assume, so that is always there, so I may not be writing all the time, but it is basically assumed to be a smooth arbitrary function of what is phi and psi. Phi and psi, again phi and psi are functions of x, y and u. Okay, maybe I can write it like this, phi of x, y, u and psi of x, y, u. Okay, see, I am assuming that my solution will be the zero set of some function small f. Is it okay? And this, the function small f is again a function of two other functions phi and psi. What are the properties of phi and psi? They are functions from x, y, u to r, of course, such that this is very important. Okay, phi of so phi of x, y, z, basically this is a constant c1 and psi is another constant c2. Okay, so basically if you look at this particular phi and psi, okay, on the solutions curve, okay, constants are solution curves of the characteristic equation, okay, equations. What is the characteristic equation? See, if you remember from earlier case, what do we have? X prime t equals to a, y prime t equals to b, and u prime t equals to c. So if you put, let's say, these two together, what is going to happen? Dx by dt by dy by dt, okay, equals to a by b. So you see, this can be written like this: dx by a equals to dy by b, and similarly if you take this, then it will be du by c. Is it okay? We can write it like this. Yeah, so the characteristic equations dx by a equals to dy by b equals to dz by c. I hope this is clear. Okay, so essentially what we have is, basically we are saying that on the solution curves, yeah, what are the solution curves? Solution curves are the solutions of this characteristic equation. You remember the characteristic equation you just wrote? They have some solution, right? that solution lies where? On the surfaces. So basically we want our function phi and psi to be constant on those solution curves. Is it okay? Okay, fine. So why do we need this thing? So basically the solution, so okay, before that let me just write it down. This thing, the solution curves defined by phi of xyu equals to c1 and psi of xyu equals to c2 are called the family of characteristic curves. I'm not writing the characteristic all the time. Characteristic curves of this equation star. Is it okay? Yeah. So once we have this, now how do we find out, how do we solve problems? And this is the thing. So basically what we have is this. Let me again recall. We have this star. That's the equation we want to find. Now what we are saying is this. This is the assumptions we are assuming. We are assuming that the solution, the general solution will look like a small f of function of phi and psi. What are phi and psi? Phi and psi are such that they will be, those functions will be constants along the solution curve. That's the only property. Okay. Okay. So let's look at it. See what is happening is this. So this is basically kind of a proof if you think about it. Okay. So basically the general solution will always look like this. That's the point. Huh? Okay. So why? See, since phi of xyz equals to c1 and psi of xyz equals to c2, okay, satisfies, okay, maybe I can put this as some equation, let's say double star, the characteristic equation, satisfies double star, okay. So what do we have? You see, d phi, yeah, the differential of phi, this is nothing but, if you remember your this thing, several variable codes, it is phi of x dx plus phi of y dy plus phi of z dz. Is it okay? So phi of z we are writing as u, so let's write it as u. So it is phi of u du. Yes, and this is going to be 0. Yes, because you see phi is constant. So if you are taking the differential, that is going to be 0, right? And so that is basically nothing but what is phi of x dx? Dx by, you see, dx by a equals to dy by b equals to dz by c, or du by c if you want, if you want du by c. Yeah. Now you see, the thing is, if you take it to be some lambdas, then dx equals to lambda times a, dy equals to lambda times b, and du equals to lambda times c. So basically this becomes a times dx plus b times dy plus c times dx du, sorry, is equals to 0. Lambda is non-zero, right? And similarly, if you look at the other equation, yeah, so this equation, similarly, that equation will give you a, one second, sorry, there's a small mistake which I did. This should be phi of x, phi of y, and phi of u. Yes, and similarly, from this other equation, you are going to get this is c psi of x plus b of psi of y plus c of psi of u equals to 0. I hope this is clear. Okay, a similar differential thing. Okay, so now you see I have these two equations, 1 and 2. Okay, I need to solve this equation. Yes, so and solve this equation for what? For a, b, and c. Yes, see, we are assuming, please understand what I'm trying to do. What I'm saying is this: if you are given this equation, then the general solution will be given by this. This is the theorem which we are trying to prove. You understand? If you are given this equation star, the general solution will be given by some arbitrary function small f of phi psi, where phi and psi are constants along the characteristic equations, characteristic curves actually. Yes. So we want to show that. So for that, we are starting with phi is constant and psi is constant. If phi and psi are constant, then 1 and 2, these two equations we are going to get. Clear? And the thing is this, now if you solve for a, b, and c, yes, what happens? So solving for a, b, and c, solving for a, b, and C, we obtain, what do we obtain? We obtain A by del phi u by del y u. Yes, this is equals to B by, this is just two equations, right? Of course, you can solve it, absolutely no issues. So, del of phi psi by delta of u x equals to C by del of phi psi by del of x comma y. Okay. Now, see, f of phi psi is given to be 0. Okay. So, what that will imply is, therefore, that will imply that p times del phi psi by del yu. Okay. One second, I wrote this is a mistake. This is phi psi. Okay. Plus q times del phi psi by del ux plus, okay, equals to del phi psi by del x comma y. Yes, this is true. So, you see, if you substitute this particular thing, this one, okay, let me put it this way. Let's say this is 1, 2, 3. This is 3. Okay. So, if you substitute 3 in this 2, okay, let's call it 4. So, substituting substituting 3 in 4, okay, we have f of phi and psi is definitely going to be 0. Is it okay? See, this is always true. The 3 you have already, we got it, right? Use solving 1 and 2. So, once we have 3, if you substitute it in 4, what is going to happen? Essentially, A will be lambda times this particular thing, B will be lambda times this, and C will be lambda times this. If you substitute it, you are basically ending up with f of phi and psi is equals to 0. Okay. So, this is the solution of star. This is what you are going to end up with. Solution of star. Okay. I hope this is star, right? That's what we wrote, star. Yes. Clear? Okay. So, this method is called the method of characteristic. Okay. Now, the thing is this. There is another small theorem which I want to do. We are not going to prove the theorem, but just write down the theorem. Okay. Theorem. So, this is the initial value problem. Okay. Or we also call it a Cauchy problem. Cauchy problem. Okay. So, you see, this is basically a theory part. I want you to know the theory, that is why I am going through it. Otherwise, you can just, get an idea of it. You don't have to worry about it so much, and then you can look at how to solve problems. You can do that. Okay. So, suppose that C is a given curve in the xy plane, x comma y plane, okay, with parameterization. This is a very, very important theorem, so please keep this in mind. X naught of t, this is actually equals to x, and y will be given by y naught of t. Okay, that's the parameterization basically. Yeah, and this t is in R. Okay, this is the curve. And suppose x naught prime t and y naught prime t are piecewise continuous. Okay. Piecewise continuous where? Wherever it is defined in I. Okay. So you see, I have defined it in R. You can define it in an interval I. Absolutely no issues. Okay. And of course, this we also need the derivatives. Prime square of that plus y naught prime square is non-zero. Okay. Also, suppose I will explain to you what this theorem is. Let me write it down. Suppose that u, which is u naught of t, is a given function on the curve. Given function on the curve C. Curve C. Okay. So this is the curve C. Then there exists a solution. There exists a solution. Okay. And how is the solution? U, which is u of xy. Okay. Of the equation. General equation, if you remember, f of x, y, u, ux, uy equals to 0 in D, the domain D, subset of R2. Okay. Containing the curve. So this D will containing the maybe I can write it here. Sorry. D containing the curve C. So basically the domain should contain, of course, curve C for all t in R. If you are writing it to be in some interval I, then that will be I. And the solution u of xt, sorry, u of xy, okay, satisfies the initial data. I know this is a very big statement for a theorem. Let me just write it down and I will explain to you. Data that is u of x naught of t, y naught of t. This is nothing but u naught of t. Is it okay? For all t in R. Yes. So what I am basically saying is this. See, let's say that you start with the curve C, right? That is in the xy plane. Yes. So xy plane is wherever we are starting. That's our initial plane, xy plane. So let's say this is our plane. This is the domain D. Yeah. This is our domain D in xy plane, subset of R2. Okay. And we start with a curve C here. A curve C. Some curve C. Okay. So now what do we expect out of the curve? See, first of all, we expect it that it is piecewise continuous. Is it okay? We expect that the derivative, of course, the derivative of the curve is piecewise continuous. See, any C, how do you write it here? In this case, we are writing as x naught of t, y naught of t. Okay. And of course, t is varying somewhere in, let's say, R. Okay. Now, the thing is, what do we want is this curve to be piecewise continuous, and we also want the derivative, the derivative of the curve has to be piecewise continuous, and we also want this condition x naught prime the square of that and y naught prime the square of that, that is non-zero. Essentially that will actually give you the guarantee that I mean there is a tangent essentially, yes, right? Otherwise if they both are zero, so basically we can't talk about it. Okay. So essentially what is happening is, now you see what they are saying is, then and you also suppose that there is a solution u, okay, on the curve C. Yeah. So basically given the curve C, there is a u which is u naught of t. Okay, right. So then you have a solution u which is u of xy, and that solves this equation, or the equation which we want to solve in the domain D. Yeah, in such a way that the initial data is satisfied. So basically u at the point x naught y naught is nothing but u naught. Okay, see, u naught is given to us. So essentially what we are doing is the we can get a curve C such that the initial condition is also satisfied along with the equation. That's what it is saying. Okay. So maybe it is better to start with one problem, and I will show you how to solve this problem. So it becomes much clearer. Okay, let's look at this example. X ux plus y uy equals to u. Yes, we'll look at various different examples for this particular topic so that it becomes very clear to you what is happening and how to solve problems. Yes, okay. So you see, first of all, how do you solve it? First of all, write down the characteristic curve. So the characteristic curve, I am taking a shortcut here. I am just writing CHAR, characteristic curves. Okay, curves of this equation, okay, are the solutions of the characteristic equations, right? What is the characteristic equation? Dx by a. What is a? Here it is x. And then dy by b. B here it is y. And then du by c, right? C is u here. So those are the characteristic equations. Now if you solve this equation, basically what you are getting is this. You see, you can write it like this. So how do you solve it? You see, you can just, I mean, you can do it in rough. You don't have to do everything here. You see, this is dy by dx is nothing but y by x by y, right? X by y. Dy by y, so y by x. Yes, y by x. Now you can just solve it, right? You can see that it becomes dy by y equals to dx by x, and you can solve it in all these equations. Yeah. So solving this equation, what do you get? We get phi. You remember we get, you see, in this original problem we have this small f of phi and psi equals to 0. That's our general solution. Huh? So in this case, what is our phi? Phi we will be defining it to be y by x. Yeah, and this is C1. Clear? So this system, so solving this system, we get this, and we can define psi. Psi is what? Psi is u by x. That is yours C. Is it okay? U by x, which is C2. How do you get it? You just solve this equation again. As I told you, dy by y is log y, right? Mod log y equals to mod log x plus some constant c. So basically this is log of y by x equals to constant. So basically y by x is some constant k, e power c, which is some constant k. So now the thing is this, you see, what we are doing is we are defining this as my new function phi. Yeah. And the thing is this, you see, this solution, y by x equals to constant, this actually solves star. So basically this solves the characteristic equation. So basically on the characteristic curve, y by x has to be constant. You understand? So if I am assuming my capital phi to be y by x, then on the characteristic curve it is constant. You see, we want our phi and psi, you see, we want our phi and psi to be constants along the solution. So basically along the characteristic curves, we want them to be constants. This is what exactly is happening here. You understand? This is just a trick way of writing it. Okay, where C1 and C2 are arbitrary constants. Arbitrary constants. Okay, let me solve the whole problem and I will again explain to you what is exactly happening. So therefore, what is the general solution in this case? If you remember, general solution is small f of y by x and u by x equals to 0. You see, the general solution is f of phi psi. You see, f of phi psi equals to 0. Okay, so exactly what are we doing here? Let us again understand. This is the equation given to us, right? Okay, what is our a? A is x. What is our b? B is y. And what is our c? C is u. Okay, first of all, once you have the equation, you can always write down the characteristic equation. So what is the characteristic equation given this equation? Characteristic equation is given by this star. This star. Okay. Now, if you solve star, so solving star, what do you get? Solving star, we get the characteristic curve. Characteristic curve, right? Once you solve the star, the curves which you are ending up getting, because you remember x, y, u, these are function of some parameter t, and this actually is on the curve C, right? So you see, we want, so basically our general solution is f is an arbitrary function, f of phi psi equals to 0. Smooth function, of course, f phi psi equals to 0. Now this phi and psi, we don't know what those phi and psi's are. Yeah, only thing we know is phi and psi, this is from R3 to R. Okay, and what is the property of phi and psi? The property is phi is constant and psi is also a constant, let's say C2. Constant along what? These are not constant functions everywhere. These are constant functions only along the characteristic curves. These are constant along the characteristic curves. Okay. So you see, the thing is, if you solve this star here, by solving it, we get y by x equals to constant. So basically, if you are taking phi to be y by x, so phi is constant along the characteristic curve. Again, solving these two, you are getting psi, you are getting y by u by x is constant C2, right? So if you are taking psi to be u by x, then psi is constant along the characteristic, right? So C1, C2 are arbitrary functions. Now this is your phi and psi. What are those? These are functions. See, do you understand this? Phi and psi are not constant functions. They are constant only along the characteristics. Okay, characteristic curves, that is. Okay, so what is the general solution in this case? General solution is given by f of y by x and u by x equals to 0. Okay, right. Now if I'm, let's say, if I'm asking you what is the particular solution of this equation, particular solution. Okay, let's understand this thing. So you see, for a particular solution, f is a smooth function. So you see, f is in C1 here, given f is C1. So f is an arbitrary function in a, arbitrarily smooth function. Okay, so you see, f is a function from, if you think about it, this is in R2 to R. That's the function, and essentially the general solution is a level set of this function essentially, and the general solution is f equals to 0. Yeah. So basically, we are saying that there are some points in R2 given by this such that f is 0, and that will give you some set, right? That set is our general solution. Is it okay? Right. So now, how do you find? How do you find a particular solution? Of course, you can think of it like this. See, if you take f of, let's say, I don't know, maybe W1, W2. Yeah, think of it like this as W1. Yes. Now, if you do that, then this thing becomes f of y by x and u by x. This is equals to 0, implies y by x equals to 0. Okay, that will give you y equals to 0. That does not give you anything. I want to get u out of it. So basically, if you take this to be W2, so essentially what do we get? We get, if you get W2, then you get, this becomes w by x equals to 0. Sorry, not w, u, sorry, u by x. So it becomes u by x equals to 0. Okay, that will give you u is equals to 0. So that is one particular solution. See, if u equals to 0, this is 0, ux is 0, uy is 0, ux is 0, the whole 0 is equals to 0. So that's the general solution. Okay, you can also find other solutions out of it. Yes, if you think about it, let's say, let's give you another solution which is a nice solution, and let's see if that is a solution or not. Okay, see, let's say f of w1, w2 to be, let's write down a simple one, maybe w1 plus w2. It's a very arbitrary function but smooth function, right? It is C1. Okay. Now, you see, the general solution is w1 plus w2 is equals to 0. What is w1? It is y by x plus u by x is equals to 0. So essentially, u of xy equals to minus y should be a particular solution, is a particular solution according to this, right? Okay. Now, is it really true? Let's see. See, if u equals to minus y is a solution, particular solution, let's look at the equation. See, x times u of x. What is u of x? If u is minus y, u of x is 0. Plus y times, what is u is minus y? U is minus y. So what is u with respect to y? It is minus 1. So this is basically minus 1 y, which is u. So you see, that solves the problem. You understand? So the thing is this is how you find particular solutions, but essentially this is the general solution of this. And f is a smooth function continuously differentiable C1, any arbitrary function, arbitrary, yeah? Let me write it this way. I hope you have understood what exactly is going on here. Okay, let me give you another example. It makes understanding it much better. Okay, so example 2. Let's say you have this equation x ux plus y uy. We are just starting out with very simple problems, yeah, so that we do not, get confused here. Let's say, okay, maybe you can, yeah, x, this is the problem we already did, right? So maybe x square ux plus y square uy equals to x plus y times u. Let's look at this problem. Is it okay? So first of all, how do you do it? First of all, you find out the characteristic equation. What is the characteristic equation? If you remember, it is dx by a. What is a? X square. And then dy by b. What is b? Y square. And then du by c. What is c? X plus y times u. Yes? Okay. So these are the characteristic equations. See, now what is the general solution? The general solution is, we have to write it like a function, arbitrary function of phi psi equals to 0. Yeah. Now what is phi and psi? Again, phi and psi are functions from R3 to R. So functions, of course, but there is a particular property of this function. What is the property? The property is this: phi and psi should be constants along the characteristic curves. Okay. So how do you find the characteristic curves? You solve this equation. You solve. So this is the characteristic equation. Solving the characteristic equation, we get characteristic curve. So from the first two equations, what do you get? We get this. Let's put it this way. From the first two, we get 1 by x minus 1 by y equals to some constant c1. Yeah, you can easily see this is always true, right? I don't have to calculate explicitly. This is always true. Okay. Now, again, so one has this. So from first two, let me write it this way. From dx by x square equals to dy by y square. Okay. So this is what we get. Again, from star, what do we get? From star, we get dx minus dy. We can write it like this, right? If you remember your algebra, right? Simple algebra. Dx minus dy by x square minus y square can be written as du by x plus y times u. Right? We can do it like this. Okay. If we can do it like this, you see, this will imply the d of x minus y by x minus y equals to du by u. We can write it like this. And that will actually imply x minus y by u is c2. Clear? Okay. Again, you see, using these two, let's call this 1 and let's call this 2. Yes? So using 1 and 2, okay, we get xy by u is c3, a constant, another constant c3. Yeah, it's very simple, right? We just put 1 and 2 together and we get this equation. So you see that therefore the general solution is given by small f, okay, of phi and psi. What is phi and psi? You see, if I am assuming my phi to be this one, then phi is constant along the characteristic, so it is xy by u. Okay, what is my psi? Psi I can assume it to be this one, right? X minus y by u. This is equals to 0. So that's your general solution given f in C1 is arbitrary function. Is it okay? That's your general solution, and hence this is how you solve this equation. See, the thing is, this is please understand this. This is a general solution. You can write it in many different ways, right? It's not like this is the only way we can write it. Yes, we can. This is how we wrote it. You can just use this one and write it. Yeah, you understand what I'm saying? you can use the 1 and 2 and write it like, let's say u equals to, from here what do you get? X minus y by xy. So from 1 you get x minus y by xy equals to c1, right? So here what do you get? X minus y is u times c2 by xy equals to c1. So basically you get u by xy equals to c. This is the same thing, right? So okay. Anyway, so we can do it like this. So essentially what I'm trying to say is this. You can just write u as a function of xy, and then another function of x minus y by 2. That's not an issue. Okay. But this is the general solution. That's all. So with this, we are going to end this lecture. In the next lecture, we'll look at more such equations and how to solve those equations given an initial data. Thank you.